Welcome to part one of a study of chapter 35 from Halliday, Resnick, and Walker's Fundamental of Physics. Chapter 35 is on interference, and up to this point, that is to say through chapter 33, we've looked at propagation of a ray that involves the ray moving in a particular direction, here denoted by the unit vector k, and the electric and magnetic fields being perpendicular to k. That is to say that the wave is transverse. So E dotted with k is equal to 0, B dotted with k is equal to 0, and likewise E dotted with B is equal to 0. But in order to understand lenses and mirrors, we don't need to actually worry about E and B unless we want a theoretical basis for the observations that have been made. The ideas of focal length and angle of reflection equals angle of incidence and Snell's law can be observed phenomenologically and don't have to be proven. However, we're going to shift our scope in this chapter to look at the waves itself. And so we're going to look at the wave properties. And along the way of doing this, we're going to prove Snell's law. This is something that we didn't do in chapters 33 and chapters 34. But we're going to go ahead and prove it here. And so we're going to think of the wave as idealized in terms of only the electric field. So we're only going to look at how the electric field moves. It just makes the problem simpler by reducing it to 2 dimensions. So again, we have a direction of propagation denoted by this unit vector, and the electric field denoted by this trace has peaks here and here, and troughs likewise here and here, where the electric field takes on its vector magnitude maximum. And the trough, of course, is the same maximum, but directed in the other direction. So as the wave propagates, what we're going to be interested in eventually is what happens when we have more than one wave, or what happens if we split the wave in some fashion. And so interference is all about this idea of having 2 individual waves, the black and the orange pictured here, and how do you add them together? So if they are in phase, that is to say they're going to produce constructive interference, then their peaks line up. And they add just straightforwardly. So the peak of the black adds to the peak of the orange, the trough of the black adds to the trough of the orange, and so on. And you get the blue wave, which is the sum of the black and the orange, who has an amplitude larger, and in this particular case, the exact sum of the amplitudes of black and orange. However, if the waves are out of phase, then what ends up happening is that the peak of black coincides with the trough of orange. And in the case that I've tried to picture here, if their magnitudes are exactly equal to each other, then the sum total is not the 2 amplitudes added together, but the 2 amplitudes subtracted together. And so blue in this particular case, which is again the sum of black and orange, is identically equal to 0. The 2 waves completely cancel out. So we're going to be talking about exactly how do we create interference, either constructive or destructive interference between waves, and the particular ways in which we handle the situation when the waves are not exactly precisely 100% constructively or destructively interfering. So your book covers things in a slightly different order than what I'm going to do here. What I'm going to do here is just give a general overview of what we're expecting to see, and then down the road we can drill down on some famous experiments that demonstrate these. So we're in order to decide what in phase and out of phase means, we need to measure phase differences in between the waves. And typically, we'll measure phase differences in three separate ways. So we can measure them by degrees, where the destructive wave, the constructive waves have their peaks aligned, and they can be offset from each other by 0 degrees or 360 degrees or minus 360 degrees or 720 and so on. And I'll show examples below to understand why you might want 360 or 720 or vice versa. Likewise, for the destructive waves, the degrees will be multiples of 180, 180, and then 180 plus 360, which is 540, and so on. Typically, we think in degrees, but we have to calculate in radians. So it's natural to transfer the degrees into radians. Constructive are 0 and multiples of 2 pi. And destructive are odd multiples of pi. So pi, 3 pi, minus 3 pi, and so on. But almost always, in order to calculate degrees or radians, unless we can just inspect the diagram like we did in the ones above, typically what we really have to do is count wavelengths. So if we have constructive interference, we have the number of wavelengths, which is denoted by capital N in your book. N has to be an integer. And if it's 1 or 2 or 3 or 4 or minus 1 wavelengths, then the waves are constructively interfering. And if they're half integers, they're destructively interfering. So numbers like they differ by 1.5 wavelengths or 3.5 or 13.5, 7.5, minus 2.5. All of these are examples of destructive interference. Now, there are three ways of getting phase difference. And I will always use the abbreviation PD for phase difference. I think sometimes your book uses it for path difference and sometimes for phase difference interchangeably. So just be aware of that. So here's an example of a path length difference. Both green and blue sources emit at the same wavelength. And the green just happens to be further away from the screen than the blue one. It's 1, 2, 3, 4, 5, 6 wavelengths away from the screen. So N green, which is the number of wavelengths between green emitting the wave and the screen receiving the wave that green emitted, is equal to 6. And likewise for blue, you have 1, 2, 3, 4, 5. And so N blue, which is the number of wavelengths between the source that where blue is located and that it emits the wave and the screen where it receives it, as 5. And so in this case, the path difference is the absolute value of N green minus N blue, or N blue minus N green, as anybody likes. And this path difference is 1. That is to say that the wave from green travels a full wavelength further than blue does. And so this is constructive interference. Now notice green is located at minus 0.2. If we go ahead and move green up just a little bit to minus 0.1, and we again put the screen in and we look at it, we find that the green wave goes 1, 2, 3, 4, 5, 6 peaks, but it doesn't make a full wave before it hits the screen. So it actually turns out that green is 5.5 wavelengths away from the screen, because the wavelength of green and blue is 0.2. So moving green up 0.1 chops off half the wave. And blue, we haven't changed at all. It's still the same thing it was in the example above. It's still 5. And so when we look at this, the phase difference is again n green minus n blue, or n blue minus n green. Again, it doesn't matter, but it's 1/2 a wavelength. And so this is destructive interference. And we can confirm that by looking and finding that, for example, right here, this trough is matching, or I should say canceling, this peak. And so this combined wave is actually 0, that every time green pushes in one direction, blue is pulling in the opposite direction, or vice versa. Okay. We have a second way of getting a path difference, or excuse me, a phase difference. And this is a phase difference due to a medium. So I've taken the same situation before. I've allowed these waves to propagate a lot more, but we've introduced a medium denoted by this sort of gray area right here. So you can think of this as some kind of slab of glass or oil or something, but the green wave comes into the medium and it slows down, which means that, and we'll see this down below, that its wavelengths bunch up and it comes back out. And if one zooms in into the section right where the slab is, I may not draw it like there, but basically this is the area where the medium is, then we can see that there's more wavelengths of green, now denoted by red, just to distinguish that it's inside the medium, than there are blue. But if we put the screen back out here, we'll see that again, we get a peak coinciding with a peak. So for green, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 inside the medium, 10, 11, 12, 13, and 14. So n green here is equal to 14. And blue is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. And the phase difference between these two, just for fun, we'll do n blue minus n green. Again, it doesn't really matter since we're taking the absolute value. And this is 3. And so this is constructive interference. And so we can, without moving the sources relative to each other, like we did in the earlier example, we can actually just move the wave, as it were, by inserting a medium that causes a different number of wavelengths to travel through the same geometric length that we would measure on a ruler for one of the waves than for one of the others. All right, our final example is reflection. It turns out, and this is complicated to prove because we have to go back to Maxwell's equations and look at the boundary conditions on an electromagnetic wave reflecting from a surface like a metal or glass. But it turns out that waves, when they come in and reflect off of a less dense medium, stay in phase. So less dense stays in phase. And so if we have a wave that comes in and reflects, it comes back out, and the reflected wave is not destructively, but rather constructively interfering with the incoming wave because every peak and every trough line up. And you can count up the number of wave differences, but we'll see later that it's just better to account for it as a 0 or a 1/2. The 1/2 coming from if the wave reflects off of a more dense medium. A more dense medium causes a half wavelength shift, or a 0.5 for capital N. So now the peaks and the troughs, or rather the troughs and the peaks in the way that I've marked them, in the order that I've marked them, are lined, and so this is destructive interference over here. So over here is constructive, and over here, destructive. And the place that will predominantly apply this are for thin films, thin optical films that are typically put on optics that produce a phase shift off of reflected light. And so this is a way in which, as we're filming people, say, wearing eyeglasses, we can minimize the amount of reflected light in their glasses. So if one watches Japanese anime, they typically denote a character wearing eyeglasses as basically having two white discs that totally obscuring their eyes to indicate that the glasses are reflecting light. We don't want that. We want effectively the glasses to look like two hoops with nothing in them so that the light doesn't reflect off of the glasses. And this idea of thin films is extraordinarily useful, and we'll come back to that. Okay, with those preliminaries out of the way, what we're going to do now is we're just going to start into chapter 35 proper with section 35.1. And we're going to talk about light as a wave. And the unifying principle for light as a wave up to Maxwell's equations, which were around 1865, give or take, is this idea of Huygens principle. And Huygens principle is still germane for Maxwell's equations. It still helps guide things. And in fact, it actually helps guide quantum mechanical waves as well. You can see into the 20th century, people using Huygens equations to understand what was going on, or Huygens principle to understand what was going on in the kind of wave mechanics that happen in quantum mechanics. All right, Huygens principle was proposed in 1678 by the Dutch physicist Christian, I think, Huygens. And when he proposed that light is a wave, and it allows us to explain refraction without needing Maxwell's equations, because of course, Huygens lived 200 years approximately, or before Maxwell had his stroke of genius. So what we're going to do is we're going to reduce our wave. Instead of paying attention to peaks and troughs, we're just going to indicate the location of a peak. That's the usual meaning of the bar, although it could be a trough. And the peak form the wave fronts. Of the wave. And the wavefront of the wave is always perpendicular to the direction that the wave is propagating. Again, K is the direction of the wave, and that just reflects that the electric field is perpendicular to the direction of propagation. And that is to say that, again, the wave is transverse. All right. Now, Huygens principle reads as follows, and I've included a figure from your book. The principle reads, all points on a wavefront, that is to say that vertical magenta bar that we were looking at just above, and we'll look at over on the right, all points on a wavefront serve as point sources of spherical secondary wavelets. After some arbitrary time, t, the new position of the wave will be the surface tangent to the secondary wavelengths. The process then repeats over and over again. So your book offers this sort of picture where each of the wave, or each point on the wavefront represents a little source that sends out spherical waves. To be clear, your book and I and anybody can only give you a finite sample of those. Here your book gives 5. Here's the wavefront at time t equals 0. And you can think of there's some sort of extending wave that eventually gets out to this new wavefront at time t equals delta t. Now that may not be easy to really see. I broke down some frames, as it were, individually. So at time t equals 0, the excuse me, the wavefront starts propagating little waves. And so here we have t equals 0 plus a tiny time, let's call it delta t1. The waves have come out a bit, but they haven't peaked. These are now waves that are trending down to their node or at the halfway point, a minimum, right? So this would be where the trough or the minimum is. And I'm just sort of highlighting it, or not highlighting, but whispering that piece in there gently. Okay. At some time t equals 0 plus delta t2, where delta t2 is greater than delta t1, the waves have now passed that midpoint and are growing in strength again towards the peak. And then finally at t equals 0 plus delta t3, where delta t3 is now greater than delta t2, the waves have gotten out sufficiently far ahead and are at their peak that we now identify the new wavefront. And this process just continues to go. So we could have taken the minimum and assumed wavelets were being produced there, or so on and so forth. So don't try and think too deeply about how you would visualize Huygens principle. It's not terribly easy to do, but this is the general gist. And the reason this is particularly useful in guiding is because it'll help us prove Snell's law. But before I go ahead and I do that proof, it's important. I've recopied the principle down here again. This is a picture your book includes where there's some paddle back here that is driven by a motor to go up and down, and it produces straight or nearly straight water waves. And then right here, there's a solid wall with only a small opening. And so these straight parallel waves hit the beach, as it were, break against the barrier, and what's produced is these spherical waves out the other side, or cylindrical in the case of water, because there's a flat surface where the water meets the air. And no doubt Huygens had seen this, and this prompted his principle, because effectively this area in here, let me use a different color. This area in here, that area is basically serving as all the little spherical wavelets. Okay. So how do we prove Snell's law? Your book offers figure 35.3 as the method for doing that. And the one key assumption that we talked about in a phenomenological sense in chapters 33 and 34 is that wave slows down when it comes in a medium. So we're going to assume that we have light coming in air. I appreciate that for all intent and purposes, the speed of light in air is almost the same as the speed of light in a vacuum, but it's not quite. So the speed of light in air will be v1, and that speed will be greater than the speed of light, say, in glass where it's entering. And so you can see this wave comes in here, and because it's coming at an oblique angle, when part of the wave hits, it slows down. And in slowing down, it effectively has to turn the wave fronts. They have to, in order to keep up, they hit the glass and they slow down. And so as we progress, more of the wave enters and the direction changes from being like this outside to being like this inside. If we redraw that second vector here, we see that the wave of the propagation direction moves away from the normal. And because the direction of the wave front moves away from the normal. And so the direction of propagation actually gets closer to the norm. And that's the phenomenon we expect from Snell's law, that the wave, when entering a denser medium, bends in towards the normal. And then the refracted wave just continues on and becomes fully established in the medium as it sort of diminishes or exits the air. So this would be if we had a finite wave pulse that went from the air into the glass. Now, in order to prove Snell's law, we're going to focus in on this middle plane. And there are two triangles to pay attention to. There's the triangle from H to E to C. And if you take a look at that and redraw it so that it's not sort of laying on its side, you'll quickly come to conclude that D, which is the common distance between H and C, D sine theta 1 is equal to lambda 1. And likewise for the blue triangle, which is H and G and C, you come to the conclusion that D sine theta 2 equals lambda 2. And obviously you see where this is going, but let's just take our time and get through it. So if we solve for D and equate, solving for D just means we divide by the respective signs on each of them. We get that from the top equation, lambda 1 over sine theta 1 is equal to D. And from the bottom equation, lambda 2 over sine theta 2 is equal to D. So if we equate those two, we see that theta 2 over sine, lambda 2 over sine theta 2 equals lambda 1 over sine theta 1. And that gives us one equation. What we want to do now is eliminate the wavelengths because we don't normally see the wavelength. We have to infer the wavelength from some other measurements. But we do see how fast or slow light moves through the medium. And so for that, what we can do is just analyze the amount of time. So the amount of time it takes the wave front that is coincident with the point E to travel to the point C is, well, it has to go lambda 1, and it's traveling at v1. That's its speed. So the time elapsed to go from E to C is lambda 1 over v1. And you can make the same argument. How long does it take to go from H to G? And that time is lambda 2 over v2. And those times have to be the same because the peak of the wave on this bent wavefront and the peak of the wave here and here, that these peaks all have to be happening at the same time. And so those two times have to be equal to each other, and setting them equal to each other and eliminating delta t gives us that lambda 1 over v1 equals lambda 2 over v2. So we can combine these two equations. The first thing that we can do is we can solve this equation and put it into a different form, which is we will cross multiply v1 up to be on the side with v2, and we'll cross multiply lambda 2 down so that lambda 2 is on the same side as lambda 1. And we now have that v1 over v2 is equal to lambda 1 over lambda 2. But now we can go back to our geometry that we just did in terms of the distance d between h and c on this line on the interface, that is from h to c. And here what we'll do is we will cross multiply lambda 2 down and sine theta up, sine theta 1 up. And so we get that v1 over v2, which is equal to lambda 1 over lambda 2, is equal to sine theta 1 over sine theta 2. Now, we'll just cross multiply again, bringing sine theta 2 onto the same side of the equation as with v2 and sine theta 1 with v1. And we get that sine theta 1 over v1 equals sine theta 2 over v2. So it sort of looks like Snell's law, but we like to think of Snell's law in terms of the index of refraction. So to get that, we multiply both sides by the speed of light. And for convenience, I just put the speed of light over v1 and left sine theta 1 on the side, and likewise on the right-hand side with c over v2 and sine theta 2. And we recognize that this quantity is the index of refraction for medium 1, and this quantity is the index of refraction for medium 2. So what we've effectively done is, using Huygens principle, we now have at least a deeper theoretical understanding of Snell's law than just observing it. Now, there's one more result that shows up from this kind of computation. We can milk the lambda 1 over lambda 2 equals v1 over v2 equation, and remembering that for any wave, the product of its wavelength and its frequency has to be equal to its speed. We can solve for lambda 1. In other words, we can say that lambda 1 is equal to v1 over f1. And we can plug that in right here. So lambda 1 equals v1 over f1 goes right there. And likewise, lambda 2 equals v2 over f2 goes right there. And now we can just clean up the equation a little bit. Let's bring the frequencies out in terms of their ratio. F2 is in a denominator, so it becomes a numerator. F1 is just in the denominator in the numerator, so it stays as a denominator. And we get the ratio of F2 over F1. That has to be equal to V1 over V2. But that's only this side of the equation. That's the side right here. It still has to equal V1 over V2 over here. And so the only way that that ratio of those two frequencies times V1 over V2 can be equal to V1 over V2 is if the frequencies in ratio, that is to say F2 over F1, are equal to 1. And that is F2 equals F1. And the frequency never changes. So at this point, I'm going to stop with the math and just point out a couple things. In part two, we're going to see that a phase difference due to path length is going to be observed by Young's famous double slit experiment. And the double slit experiment, it's hard to overemphasize how it shaped thinking about physics worldwide. It still does. And then we're going to get a phase difference for a medium and reflection for thin films. And again, it's very difficult to overemphasize the practical importance of thin films. They show up in a variety of places in industrial settings. And then we'll talk about putting it all together, or at least partially putting it all together. It won't be precisely thin films. And that is phase difference with three pieces. That is to say, path length, medium, and reflection. And this will be the Michelson interferometer. And the interesting history of the Michelson interferometer is it killed the idea of the ether, the so-called mythical substance in which the electromagnetic wave propagated. And in doing so, it ushered in the theory of relativity. So that's all for now. Good luck, and we'll talk to you next time.